Okay, so now recording. I guess I can be the chair and introduce you. So today for Gregorius Winter's first inaugural series talk in the series, we're very happy to have Kasra, who's going to be telling us about an introduction to entanglement cohomology. So please take it away.
Okay. Yep. So like Ferko said, we're going to be doing an introduction to entanglement cohomology, and this is kind of what we're going to go through, right? First, our purpose and goal, like why we're here. I'm going to really start from the basics, like states, Hilbert Spaces. Then we're going to go to these things called entanglement K-forms. I'm going to like very quickly define what cohomology and what like co-chain complex is. And then I'm going to go to the bipartite complex, which will lead us into a 2-qubit example. And, first, thank you to Ferko, Greg, and Ishan for letting me join in the project like rather late. I'd also like to thank like the people that like helped with me understanding the subject and kind of just also editing the talk and making sure the typos were fixed. I really hope this talk is a good introduction for everyone that's attending, which or watching, because we're going to see later that Ferko, Ishan, Greg, everyone, there's going to be more talks on this subject, and I kind of just want to provide an introduction. More on that, we're here because the recent paper by Greg, Ferko, Ishan, and I, which is on archive right now, the super base paper by Tom, where the paper by Greg, Ferko, Ishan, and I comes from, right? It originates from there. And the future talks by Greg, Ferko, and Ishan. So our purpose and goal is summarized here. We want to define, understand, and explore the basic concept necessary to being able to understand what the entanglement complex is, and hopefully use a 2-qubit example to help in this. So starting, I'm assuming very little knowledge, so we're going to start with what like the rough idea of a qubit is. A qubit can kind of just be understood as this little guy here. So think of it as like analogous to a classical bit, right? Where you have 0 and 1, and it's some combination of these with some constants alpha and beta. So it's kind of just like think of it as a combination of these kind of like classical analogs, I guess. And this notation with this little guy, it kind of might be unfamiliar. It's called Bra-Ket notation. The way you understand Bra-Ket notation is that this guy is a vector, and in this case, a vector in Hilbert space, and a bra just is the vector dual to that ket vector. Now, you might be asking what a Hilbert space is. It's just an inner product space. It's at least in finite dimensions, which is all we're going to worry about right now. So now maybe we want to look at a bipartite Hilbert space, which we can kind of understand as this little decomposition, as the tensor product between two subsystems, HA and HB. And these have dimension dA and dB, respectively. So just think about it as this sum here. But notice that this also looks sort of similar to how we understood the very basic understanding of a qubit, where we have these constant expansion coefficients and these bases, right? If we look back at how we define a qubit, they look sort of similar, right? And we're going to have to use some new notation, because when we get to larger spaces, we're going to kind of have we'll call it an n-partite Hilbert space, which is just this product of n subsystems, right, which are each Hilbert spaces. And we're going to underline the indexes that the indices that index the subsystems, right? So instead of having just these like 1 to n, we're going to have underlines under them so that we know they're referring to subsystems. So when we go back, when we try to understand what a state and partite Hilbert space might look like, expansion would look sort of like this, right? Where we have these sums, these bunch of sums, right? N sums, and this massive coefficients and these, right? But that's really long. It's not really useful to write this out all the time. So we're just going to use what's called condensed sum notation. And when you see this, you should understand that this and this are the same. So really quickly, right, I think we've kind of just stated some definitions, and the talk has to do with entanglement. So I imagine the question right now is, what is entanglement? Like, what actually is this thing supposed to be about? So I think the best way to start to answer that question is by first asking what we think when we hear entanglement, and maybe asking ourselves what it might look like for some state in a Hilbert space. So now I've got a little idea board here. Does anyone want to volunteer and offer an explanation of what they think entanglement is? I just see. Particularly Kasra, since I think the other two here would probably be a little unfair. But if yes.
So pretty much we have a Hilbert space of those two systems, and that describes like a two-partite Hilbert space. And what entanglement is it's like when you can't defactorize those two Hilbert spaces.
Right.
Just like a product.
Okay, yeah, that's pretty much exactly it, right? But then that is exactly it. When we have, first we would look at what not entangled means, because entanglement is kind of just not being entangled. That was a really weird way to phrase it. But first, just understand that if we have a state in an Bipartite Hilbert space, it's a product state if we can kind of break it up into these parts, right? For some collection in these subsystems. And all entanglement is just a state is entangled if it is not a product state. All you need to say. Now, we're going to move on to a few other ideas that that don't really seem directly correlate with entanglement, but we have to use them later. So first of these is the density matrix. The first way to understand density matrix is what we call a pure state density matrix, where it's just this ket, this bra, right? But sometimes we're not going to have this. We're going to have a mixed state density matrix. Here's a generic density matrix, but you understand it as just the sum of it's kind of just like a combination of pure state density matrices, right? So you have this pure state density matrix, and think of this as kind of like a probability, right? Because it's all going to be greater than 0, sum up to 1. And we say that if this n here is greater than 1, it's called a mixed state density matrix. And if it is 1, it's literally just a pure state density matrix. Now, sometimes we're going to need to project things onto the image of P. To do this, we're going to use support projection operators, which in the case that we have pure state density matrix, I think, obviously the density matrix is the exact same thing as a support projection operator. But in the case of a mixed state density matrix, you have to do a little more. You want to diagonalize, and all you're going to do, drop this lambda, and it gives you the support projection operator. So there's also when we come to Bipartite spaces and we have operators, sometimes you want to get an operator in Bipartite Hilbert space to give us an operator in n-1 partite Hilbert space. What we want to do is use the partial trace, so we want to partially trace out a subsystem. So when we have an operator and we have this expansion, all we want to do to get the partial trace with respect to some subsystem is take out the trace of these guys here. So all we do is find this guy here, trace them out, using the standard trace in the subsystem, and that gives us our partial trace. So there's a little bit of notation, because when we talk about the partial trace, especially on a reduced density matrix, we just want to get rid of the index that has been traced out. So we would say like the trace with respect to subsystem 3 of row 1, 2, 3 is just row 1, 2. So we just get rid of this third index here. We're going to start talking about entanglement, because those are kind of like the whole crux of what we're doing. But these will tell us is sort of what's going on between a state in Hilbert space and some operators acting on that Hilbert space. And the state in Hilbert space is just kind of represented by its density matrix. To do that, we first have to have some operator that's going to first have something that restricts our operator, its action entirely to the image of P, rho. So what we're going to do is kind of restrict what's going into the operator and restrict it out of the using support projection operators. And we call this the restriction operator. Of course, with respect to whatever density matrix we're working with. And here we're going to introduce these entanglement forms. And first, we're going to work with this case. These we have two ends. All it is operators associated with this density matrix. We take these operators that are linear operators on n-partite Hilbert space, and we just use the restriction operator on them, right? So we just put the support projection operator on the left and support projection operator on the right. All we do. And so an element is just going to be, well, actually, I think we'll talk about that next slide. So then there's a more general idea of if we have two different things here, imagine like k is less than n, then we kind of ask ourselves, okay, what is this? Well, first we have to think about the n choose k ways, we can have this sort of guy here, right? So because we're taking some subset of length k from the set of length n, we have n choose k different versions of this, where all we're doing is taking this guy up here and simply restricting it to some subset, where, of course, again, just the linear operators on this Hilbert space, restricted with the support projection operators for this density matrix. So the way to think about it is the tuples of the n choose k ways, we have this. So all it is we have this Cartesian product of all the k length subsets of 1 through n with this. And the name we give this guy here is an entanglement K form. Right? Sounds like a really fancy name. But the relation to entanglement right now might not seem super clear, but it will be later when we talk about the entanglement complex. So to do this, I'm going to kind of want to work through an example. So when we go with some omega 3 is in this 3 form, entanglement 3 form, right, with rho 1, 2, 3, so it's tripartite example. All we need to think about is that we just need to use the first guy on this slide here, right? So it's just going to be some linear operator restricted by the support projection operators of rho 1, 2, 3. So all we get is just one operator restricted by the support projection operators of rho 1, 2, 3. Right? So nothing too complicated there. However, it gets a little more interesting when we have this case, right? Omega 2, but we have rho 1, 2, 3. So we have some k and n. So k is 2, n is 3. So what we see now is that we have to use what we talked about before, where it's going to be a tuple of restricted operators. So one of these operators comes from this guy, another from this guy, another from this guy, because these are all the length 2 subsets of 1, 2, 3. So we get one operator from here, one operator from here, and one operator from here.
It could be worth pointing out that this is really similar to like normal differential forms.
Right. That's where the notation comes from.
Yeah.
You chose this omega.
Yeah. So these two forms. This is like f dx dy plus like some g dy dz plus like I don't know h dx dz stuff, something like that.
Right. Look really similar. I think that comes up more in your talk with the Hodge star, right?
Yeah. But that's like where the name comes from.
Yeah.
Yeah.
So, does anyone want to try an example? Like, I guess it comes up to if we just leave these as kind of. Oh wait, Odium's here. That's interesting. Does Odium want to try any of these calling on the audience.
Well, he unmuted, so it sounds like he wants to.
He's unmuted. Maybe he's turning his camera on.
Stavros.
See, maybe he's just edging us right now. I don't know. Who knows? Well, at least okay. We'll go to the first one at least. So this is K is 1 and N is 3. All we're doing right now is we're just going to choose the length 1 subsets of 1, 2, 3. So it's just going to be one operator that's from like omega 1, P1, omega, not P row. So I keep messing it up. Omega 1 row 1, omega 1 row 2, omega 1 row 3, right? So it's just going to be 3 operators, a tuple of 3 operators, one of each. Now, the next one's kind of long because 2 choose 4 is like 6. So, oh, okay. So he's just struggling to the microphone, I guess, is what's going on. Poor Stavros, man.
We can say this one in words, though, I guess, for the second one, because it will be the length 6 tuple that has an 012, an 013, an 014, an 023, an 024, and an 034. There's 6 of them.
Right.
Suitably restricted.
Right. Exactly. Because I guess we can't get Stavros on this one, unfortunately. This is really quickly introducing what not cohomology group is and what cochain complex looks like, because I don't really want to go like super in depth with that for like time's sake and just everyone's sake. But I just want to at least introduce the concept so that people kind of vaguely understand what's going on. A cochain complex just looks something like this, where these are all vector spaces, right? We have some D maps, and a very important thing is that dm plus 1 composed with dm is 0, right? So if we compose these two guys, 0. These two guys, 0. These two guys, 0, right? It's very important. And the way we define the cohomology group, the nth cohomology group, is just the kernel of dn over the image of dn minus 1. So there's also duality of cohomology, but super important right now. So this is going to come up later when we talk about, especially the 2-qubit example. We'll see that this actually allows us to see if we have entanglement or not, right? So it is really useful, but you won't see it for a little bit. Until the last slide, actually. Now we're going to work in a bipartite complex. So we're just going to construct that thing we made before, but just with two of these guys. So a Hilbert space with 2 subsystems. So the first thing we see is that if we have this state, we want to create a corresponding pure state density matrix that's just obviously that, like cat and bra. And we can make this here, where we have the tuple, this...
can you hear me now?
Yes.
Yes.
Oh, he's back.
I don't know what happened.
It's okay. Well, I'm just gonna go on with this then. I mean, unless you want to go back and do the example, if you find that useful for you.
And wasn't the example just that like it would be like 3 terms, like
the first one, the second one. The first one, yeah, it is just
and the other would be like 2, and the other would be like 4 choose 2 possibilities. Like all the pairs out of the 4.
Oh, yeah, exactly.
Okay.
Okay, yes. So like you got what's going on. I trust he's a very intelligent. Contrary to what he's sending me on Instagram, he's a very intelligent man. So when we want to construct a complex for a bipartite space, a state in a bipartite space, we first obviously have the density matrix, and we're going to have this 1 form and this 2 form, entanglement 1 form and 2 form. Now, what's important is that we define also these maps. D2 really isn't that important, but D0 and D1, so that D0, if we compose them, they'll give us 0, right? I won't prove that our definitions will give you 0, but if you look at if you're curious, you can look at the paper and see why. We use a property of the support projection operators that I explain here, but it's pretty fun. It's interesting. So if you're curious, go look at the paper. But let's first at least define what the maps are. For D0, right, taking the complex number to some entanglement one form, all we do just use support projection operators on some constant complex number lambda. So that makes sense, right? Just project. D1 though is a little more complicated since the proof of the composition of D1 and D0 is 0. Since we won't prove that, I'm just going to define D1 without explaining why. D1, first you have this identity tensor 0, 2, then minus 01 tensor identity of subsystem 2.
It's
and
like
then,
a complicator.
Yeah. And then, of course, just restrict because we love restricting things. And in D2, of course, you restrict things. This is just a quick note. I don't want to go on forever. I'm not going to go through the explicit construction of the tripartite or multipartite complex, which is done in the paper. But if anyone is really curious about it, I would go look at the paper because I think the constructions are rather clear and it is interesting regardless just to look at those. But since we're also just going to do the 2-qubit example, I only really want to talk about the bipartite complex. So now with a 2-qubit example, which we're going to use to kind of just have a more concrete understanding of what's going on. So we have bipartite Hilbert space that we can have decompose into H1, H2. But H1 and H2 are both dimension 2, right? And that's what makes them qubits, right? Because a qubit is just, if I'm not wrong, a vector in 2-dimensional Hilbert space. So we have 2. So for H1, we can write these basis states. And it's the same for H2, right? You just switch this guy in the bottom. And so to give us a basis for the combined H1, 2, we get these guys here, right? I don't think I really have to explain why we get them. I hope that's fairly clear. Mm-hmm. But we're going to use 2 examples to kind of show why the complex made before is interesting. So the first, this is what we call, I'm just going to call it the product state, and this is entanglement. So you can just entangled state. So kind of looking at it, you can see why maybe like, product, I can see maybe why it's called that. And entangled, yeah, doesn't look very fun. So that's sort of, but we'll see why the cohomology group that we talked about before will tell us whether these are entangled product state. But first, we kind of want to understand like what's going on, right? So before we review the density matrices, anyone want to guess what they might be or what they might look like? I don't even know.
Maybe like an identity matrix, maybe.
Well, the density matrix is, if you think about the density matrix of the product state, my writing is going to be horrible here, so think about it as like P, and then just like that.
Like the identity,
right?
but like the rows are kind of like flipped. Maybe like
kind of like flipped.
0, 1, and 1, 0.
Oh, okay, yeah, I see what you're saying. For the product?
Yeah.
Not exactly. Look at product state looks like this.
Maybe it helps if you go back and show
the
column vector form of that state.
Yeah,
because it's really the column vector in the row. You're just taking an outer product.
Yeah, so just look at this, right? We're just taking this times, the broad version of this, right? So all you're going to have is kind of just like 1 in the corner and a bunch of zeros, I'm pretty sure.
Okay, yeah.
And then for I guess it might be a little more complicated to walk through the entangled one since it is kind of
You just add two different ones.
ugly. But here I'll just show. But like, see the product. All we do is multiply these guys, and it gives you just a 1 and then a bunch of zeros. And for the entangled state, you kind of just get like a half because all the corners are a half, or if you factor out a half, you just get 1. So because these are also pure state density matrices, right? It's just cat bra. The support projection operators are the density matrices. So we don't really have to do anything too special there to get them. Oh no, where? So now we're gonna have to, when we talk about the subsystems, we want to trace out the density matrices with respect to some subsystem. These are actually equal, which is nice. So we only have to do it really once right now. And when we look at, for example, this guy here, if we trace out one of the subsystems, it's just going to give us 2x2 matrix with 1 in the corner, right? And then when we want to trace out subsystem B, though, those half factors, we bring them out, and we have just 1, 0, 0, 1 for the reduced density matrices of the product and the entangled respectively. So now, like when we actually construct the cochain complex, I'm going to be kind of lazy and just use X as a placeholder for either P or E. So we know that the cochain complex for a bipartite example is going to look like this, right? And whether it's entangled or not. And we know that these D maps are going to be exactly the same as from the bipartite example, just where we plug in what our support projection operators are. So first, D0 is just this omega times the support projection operators. So you get this, right? And for the entangled state, it's the same thing, right? Times support projection operators, which gives you that. It's not, right? It makes sense. For the D1 map, it's going to look like this, right?
Is there a factor of a half on the...
Wait a minute. I think there should be, shouldn't there? Yeah, because we brought out the half. Yeah, I guess I just forgot. There should be a half brought out.
I guess it doesn't matter. It'll probably still go to 0. But...
I think
right.
There, because remember, there's a distinction between the density matrix itself and the support projection. So the density matrix has the factor of 1/2 and front. Because, right, but
right. Okay.
Now it's no longer the case that the support projection is equal to the density matrix. Because
right, we drop it.
Guys, right, they're mixed state density matrices.
Right, so we drop that 1/2 factor. Support projection. Yeah, so this guy dropped it. But this up here is still the same as the projection operator, so we're good on that one. Just the entangled state, the support projection operator is a little different than the density matrix.
Cool.
And then, and the D1 operator is like the same as before, right? This guy, and then restricted by whichever density matrix we're talking about.
By the way, should that second P in the previous in equation 23 in the second slide?
Oh yeah.
Should that P be an E? I guess.
Oh, that should be an E. Yes, that should be an E. That's an interesting. Yet another typo I did not catch, but yeah, it should be an E. I don't know why I put that. Probably because I copy pasted these and then was like, I'll find out the P's and E's later, and then didn't find the P there. But yeah. So we have these guys for the D0 maps. And then the D1 map, obviously it's going to look different for each one, but actually no, it's going to be the same. Sorry. But because obviously we're going from some Entanglement 1 form to our Entanglement 2 form, which is just one little operator, which is restricted. And then this is really ugly, goes to the end of the page, but this I don't think you should really worry about if you don't know what's, because it's kind of just supposed to be an introductory talk, and I didn't want to go into like some super deep ideas of what like cohomology actually is, how we would calculate cohomology groups beyond that really basic definition. So I just kind of have this slide for people that have more background on the topic, and you can kind of see like why this cohomology, this entanglement like complex is like useful for us. So when we look at our product state, the first the kernel of this map is in this map. We have a trivial cohomology group, right? Which we would expect if we're going to call it entanglement complex or entanglement cohomology. We would hope that at the end it would tell us whether it's entangled or not, and it is not in fact entangled. It's a product state, so it worked well there. For the entangled state, though, we have this kind of mess going on where we actually have 6 cohomology classes, and I think in the paper you can see them explicitly. So non-trivial cohomology. It's not a product state, it's an entangled state, right? And that's interesting, right? Because using this tool, we can see whether or not a state is entangled or a product state. Okay. Are there any questions?
It's not obvious that there should be, like, one can't just stare at this and say, oh yeah, there better be 6 non-trivial
no.
classes.
How did you calculate it?
Right, I just omitting the reasons and brevities.
Programmatically, though, like just to say that Ishan, for instance, in his talk, I think will show the Python code that we wrote to do this. So, like, at the end of the day, you can get these numbers just by like doing very simplistic Python manipulations, just literally counting dimensions of images and kernels, right? Like it's a linear algebra calculation at the end.
Yeah,
it's like a graph cohomology that you can like just with a matrix you can easily solve. Or
yeah, it's very similar to that, where, I mean, it's, yeah, you have some, I mean, the Ds are all linear maps, and you can explicitly write bases for each of these spaces of entanglement forms, so you just, like, brute force, like, take the image of each basis element and get some enormous matrix that represents, the way that D acts on each of these vector spaces, and then you just compute the ranks of these matrices, and by the rank nullity theorem, the ranks tell you the dimensions of the images, and then n minus the ranks tells you the dimension of the kernels, where n is the number of basis elements, and then you can just subtract dimensions of images and kernels to get these numbers. So even though the notation looks very fancy, at the end of the day, it's high school level linear algebra to do this thing.
Yeah, I see.
Right. I guess we'll see later what he actually. I actually don't know what was going with the program because I wasn't, I guess, involved until rather late. So I will be learning with Ishan's talk what was actually happening with the program, since I don't know. But is there any questions or anything that you want to like go over again?
Maybe what does the 6 mean? Like
6.
Like if you had gotten like 1,000, what would be the difference? Like, okay, it tells you it's entangled, but in what way? Like,
oh, so like what's like the okay?
Yeah.
So are you asking like what's like the practical difference between like the different non-trivial numbers you would get, like the different cohomology classes, in relation to like in that relationship to like entanglement?
I guess because like, okay, if it's non-zero, then it's entangled, but
right.
Why is it in this
That's
case?
actually a good question that I don't know the answer to. Because do either Ferko or Greg know that answer? Because I don't. That is a really interesting question.
Well, in this case, it sort of trivializes because there's only 2 qubits, so you either get 0 or 6. I mean, that's basically just the statement that for qubits, you're either a bell pair or you're factorized, so there's no, there's not much more you could do. But if you looked at higher dimensional examples, so if you did qubits and repeated this calculation, there are more numbers that you can get, and then the size of the dimension of the cohomology, this like the number appearing in equation 26, basically tells you what's called the Schmidt rank, if that means anything to you, the Schmidt rank of the state that you started with. So the Schmidt rank is basically when you do a Schmidt decomposition, how many states do you have to add up in order to express the state that you started with? So if it's 1, then the original state is completely factorized, so that the cohomology ends up being 0. If the Schmidt rank is 2, you get a 6, and more generally, if the Schmidt rank is S, you get a dimension of the cohomology that is 2 times the quantity s squared minus 1. So in this case, 2 squared minus 1 is 3, and 2 times 3 is 6. And so it's telling you like how entangled it is, if you like.
And is this expression the 2s squared thing derived in the paper?
I think that was already proved in Tom's first paper.
Yeah.
Okay.
From Brazil.
I mean, I haven't read either. I don't know anything.
let me but wait, I don't think I have it linked in here. I don't know why I'm going ahead and Googling it. There we go. So, wait, what, do you guys know roughly where it's proved?
It's somewhere in section 6. It'll be somewhere in the
Bipartite. Okay, let's go look. So, chain complexes.
6.4, or sorry, 6.6 probably, 50.
Yeah, I can go look. Let's see. Pure.
Yeah, there's the
Okay.
Where? Jesus Christ.
I see an s squared minus 1. That's for the
Yeah,
GNS.
yeah.
So the
That's for
GNS,
GNS.
that's a different complex than the one that we were using. If you scroll down, I think he does the commutant maybe after. Wait, I just saw it. Hold on. I just saw 2s squared minus 1. There it is. It's
there it is. Bipartite polynomials. Okay.
Okay.
Okay, yeah, so these are Poincare polynomials, which, if I'm not wrong, that's what Ishan's code is about.
Yeah, but the Poincare polynomial is just collecting all the dimensions of cohomology into some general function. Here there's only one number.
Right.
So 2 times s squared minus 1 is all you need. But, I mean, of course, if all this machinery did for you was tell you the Schmidt rank of, like, a state in a bipartite Hilbert space, it would not be very useful. The interesting thing about this is that you can repeat this machinery for arbitrary n-partite Hilbert spaces, and then it's telling you about qualitatively different types of entanglement within the larger Hilbert spaces, and that's much more non-trivial, right?
So this polynomial is only for the bipartite system.
Yes, the one on the screen now. This Poincare polynomial is only bipartite, which is why it only has one term. Yeah, the n-partite one will have more terms.
So, but do you have a general expression for the polynomial of the n-partite?
No. There are conjectures about this. I mean, he has conjectures for the form of the Poincare polynomial for some specific cases of multipartite states, like these generalized GHC and W states, but there's no general expression that works in all cases beyond the bipartite. It's just much more complicated. You get more stuff.
Yeah. Dimensions.
So does Ishan's code do, what is it like? I guess this is a question that he would probably want to answer, but he's not here. So like, what exactly does it do? Like, is it just the Poincare polynomials of like certain like states, or what's going on with that?
No, it's completely generic. So for the code, you hand in any pure state you want to start with in your parent Hilbert space, if you like, the multipart one you begin with. And then it just like brute force goes through and computes the ranks of all of the D maps for each D1 up to Dn, or however many you have, and then gets the dimensions of the cohomologies and puts them into a Poincare polynomial. So that works for any state whatsoever, which is nice because then you can start looking for patterns in these things, because since it's a closed form expression, you want to just play around and say, oh yeah, can I look for any interesting structure, which I think if you go to the last section in the Tom paper, he even has some pictures where you can see some patterns. Yeah, in this section 9. If you scroll through until you see this picture with this, like, it looks a little bit like
here?
Yeah, this guy. So this is a historical comment for the non-co-authors in the audience, but essentially this entire project started when Greg and I were reading this paper and looked at pictures of these forms, of them here, and stared at it and said, it looks like these Poincare polynomials are symmetric, right? The integers are the same if you read them left to right or right to left, right? Like on the last line, you see 13, 30, 40, 30, 13.
It looks like Pascal's triangle.
Oh, sorry, what was that?
It looks like Pascal's triangle, like.
Yeah. In this case, it is. So here it's
that was, I think that was his conjecture for this specific state, is that they like that Pascal's triangle thing like continues forever.
Yes.
But it is definitely true that we'll see later in my talk that it's true that the polynomials will be symmetric at least.
Yeah, we didn't manage to prove the Pascal's triangle thing that this holds in general, but indeed the symmetry property, like we saw this and we're like, okay, there has to be a proof of this. Like the symmetry is like it's too good to be true, because we tried this in all sorts of other states and it's always symmetric. So there has to be a reason for why there's a symmetry property. Like, come on, I mean, when there's a symmetry, it has to be because of some reason, and there is a reason, and we proved it. So that's what Greg will explain.
Okay. Is that like the main result of your paper, or?
Yeah, I mean, I guess the machinery you build up in order to prove this, I think, is kind of the main result. Because, I mean, once you build up all this machinery, this is like a trivial corollary that these things are symmetric.
Okay, I see.
Well, I guess I don't have a link here, but let me see. We pull up the here we go. So I guess that's like, where do you guys prove that? I actually don't forget where you guys prove that.
Probably the end of 3.3. It's like a corollary somewhere, right?
It's 3 point.
Hodge decomposition.
Hodge duality.
Yeah, and then corollary 3.1. Yeah, this is just the dimension of HK is the same as the dimension of Hn minus k. And once you prove everything, it's a one-liner, right? You just combine a bunch of isomorphisms.
But then that's like similar to like the Hodge star operation that.
Yeah, it's
exactly
the same. The surprising thing is that, I mean, what we did in the paper is essentially to show that everything you would expect to hold for differential forms on manifolds, like if you have a Hodge star,
like de-Rham.
Yeah, de-Rham, exactly. It works just like de-Rham, which this thing has no reason to act like de-Rham whatsoever. There's no manifolds, right? There's no derivatives. You're just taking tensor products with identity operators. So you had no reason to think that this should act like de-Rham, but it basically does.
But that was also basically the hard part, right? To make like the maps work in a way that, like, for example, the composition is 0 and stuff like that, right?
Yeah, that part's non-trivial. You have to tune it a little bit, because, I mean, for instance, there's also there's some normalization which we didn't see in this talk because we only did the bipartite case. But when you have an n-partite case, you have to actually tune the derivative operators so they involve some numerical factors. And if you don't do that correctly, then the D's will not satisfy the Leibniz rule with respect to the wedge product. We define a wedge on these forms, and you need Leibniz to work, right? So D of a wedge is related to the wedge of the D's in the right way. So yeah, there's some engineering you have to do a little bit.
Yeah, but mainly it does, like, all the definitions look like really similar. With like a few like things inserted here or there, because like obviously with derivatives, well, the reason that the Leibniz product just works for de-Rham, or like part of the proof, like involves the product rule, but obviously with these like forms, there's no such thing as a product rule. So to replace that effect, you just times by k, and like everything else just still works. And you also get Leibniz, so,
which is extremely surprising to me. That, I mean, that should not have worked. I mean, that only works, by the way, because we're starting with a pure state on the parent Hilbert space. If you started upstairs at the beginning of this whole game with a mixed state on the parent Hilbert space, everything breaks, right? So you don't get symmetry of the Poincare polynomials. I think Leibniz doesn't work. You get all sorts of weird stuff happening. But at the end of the day, that's not such a big deal because, as you probably know, for any mixed state on a Hilbert space that has some number of tensor product factors, you can always purify, right? There's a canonical purification that you could go up to a pure state on a Hilbert space with more subsystems. So what we're kind of learning here is that if you want to think about entanglement in a sort of differential form / de-Rham way, you should always purify, go to a pure state upstairs, and then work with the entanglement of the entanglement cohomologies of that pure state, because then it acts like a manifold. It's very manifold-like.
then
Is that
then if let's just until like if you say it acts very much like a manifold, then could you add more structure to it? So in the same way you'd add like a metric or something, what would be the analogy in entanglement? Maybe. I don't know.
Yeah, that's an excellent question. I mean, I tried to think about that a little bit. Like, what would an analog of a metric mean in this setting? Because like you would need essentially something to raise and lower indices. But everywhere we basically just raise and lower indices with deltas, so we're not really using any sort of metric structure. It would also be kind of weird if you could put a metric on this thing because, for instance, on a manifold, the zeroth cohomology, right? That's just like the collection of constant functions on a manifold because they're killed by D. So for any manifold, the dimension of the zeroth cohomology is the number of connected components of the manifold, right? Because you can have one constant function on each connected component. Here, for any entanglement, any entanglement complex, any parent state, the zeroth cohomology is always zero. So it can't really be a manifold because it would be a manifold with zero connected components, whatever that means. It would be some very bizarre thing.
Some trivial manifold.
Yeah, like a collection of points or something like this, which is not really like a manifold. It's just like a discrete thing. So the surprising thing is that, despite having zero bottom cohomology and zero top cohomology, which you would never get for manifolds because the top cohomology has volume forms in it. Despite that, this kind of still acts like a manifold. So I don't know. Then you can ask, okay, does that mean the zeroth cohomology was kind of fake? Like I was talking to Tom, I had dinner with Tom last week, and he said, okay, maybe this like first D operation that takes you from the complex number C into H1, maybe that's kind of fake. Maybe you should chop off the cohomology and start at H1 and just go up from there. Because then you might hope that this thing is really the cohomology of de-Rham on some actual manifold. But from my perspective, it looks very unnatural though, because like, I mean, the zeroth cohomology stars into the top cohomology with the Hodge star, and like you do want the top cohomology. So I don't know how to think about it.
I mean,
so it's like the analogy kind of just breaks at the edges of the complex.
Yes, yeah, inside in the bulk, if you like, of the Poincare polynomial, it's fine, and at the edges,
It works.
It is sort of worth noting that I think originally it was meant to be not similar to de-Rham, but similar to Cech cohomology. And then just maths, there's like all sorts of isomorphisms between. There's an isomorphism between Cech cohomology and de-Rham cohomology. So if you look at it like that, it sort of makes sense why this would sort of act similar to de-Rham.
On a manifold, though. Cech and de-Rham only agree on manifolds.
So
Here
it's
surprising because it's not. And also, I had Tom explain this to me because, like, when he kept saying it was Cech-like, I mean, it took like 2 hours at the board, but he explained to me that it's not just that it's Cech-like. It's like they're literally, if you go through this very involved construction where you define something called a pre-cosheaf instead of a pre-sheaf, and you define these like very strange operations that involve first a partition of the collection of subsystems and then taking complements of each element of the partition, and then you define these weird maps that involve taking complements of operators acting on the complements of the partition again. There's like 2 complements. So you go through this whole ridiculous song and dance, and after the song and dance has concluded, you apply the standard definition of Cech cohomology, and it agrees with this. So like this is literally Cech on some extremely bizarre, like contorted construction. But I don't think it's the right way to realize it as Cech. I think that you should forget that and think of this as the de-Rham version, and then do Cech de-Rham the way that Greg had been proposing, and you would get a different notion of Cech that looks much more natural. So yeah, anyway, I mean, I think Tom might have stumbled across this, but he's thinking about it in a way that's maybe not the cleanest.
Because it's not so straightforward. And Greg's way was just like some isomorphism between the two, or?
Greg's way is basically doing exactly what you would do on a manifold to prove that Cech and de-Rham are the same. So like you start with this like Meyer-Vittoris type sequence, which is exact, and it relates to like intersections of open sets on the manifold. Here the open sets are just collections of subsystems. And then what you do is you extend this to this so-called like generalized Meyer-Vittoris that has collections of open sets.
Yeah.
And then you form this funny double complex. And in the double complex, there's de-Rham going up and down. So the de-Rham Ds go up and down. And then you have these bunch of rows with the Meyer-Vittoris. And then at the bottom, you have Cech. And the Cech differentials, like the deltas go up. Or sorry, go right. So you have de-Rham going up, Cech going right. And then you do a spectral sequence argument, which tells you that at the end of the day, the spectral sequence just spits out for you the fact that the Cech cohomology and the de-Rham cohomology are the same. They just agree. And I think you can do that here as well. I mean, I'm like 65% convinced that it will just work identically here, which I think is very nice.
Yeah, I was I think you can, because if you start off with some n-partite state, and you split it, I don't know, let's say like the bottom, like the intersection at the bottom is some k-partite state, then you can do this. You can't get all n cohomologies. You can get up to n minus something or other, because after the kth cohomology, it all becomes 0, and then the exactness of Meyer-Vittoris fails. But I suppose you might be able to use the duality to extend it to the other half of the cohomologies, but I'm not sure yet.
Yeah, that I don't know, but if you're right, if you can get up to the middle cohomology, you're done, because then you have everything.
Yeah. So yeah, maybe you just wanna do this construction until like floor of n over 2, and then just use the duality to extend it. But I'll try and figure out the specific.
Yeah, I think that works. It's a nice math result, and then there's a nice physics result that, I mean, I think this thing is really the right way to think about different types of multipartite entanglement. Like that's a huge open problem, is just classify all of the inequivalent types of multipartite entanglement on generic tensor products of finite dimensional Hilbert spaces. No one knows how to solve that problem. People just brute force it on small numbers like 4 qubits and get these ridiculous structures where they try to like invoke, mapping this onto some geometry problem on a Calabi-Yau. They do like these ridiculous things to try to just handle small numbers of cases. But I think that this formalism will actually be the right way to solve that problem in general. It's very flexible.
Yeah, there we go.
I
I sort of have to go in 5 minutes, so if there's anything else that's interesting that anyone wants to say, then say it now.
Yeah, I probably gotta go too. But I guess half the people here kind of joined like in the middle and probably late, so they've probably been talk on you, Ferko, and Odin talk about the kind of weirdness of it all. I guess I don't know how else to say it.
It was
Just like I don't know how to use kind of just
This is the fact that it acts like de-Rham, you're saying?
Yeah,
I mean, it's surprising. I mean, often when it has this structure, like this, the same thing happens when you do this BV-BRST quantization in, say, theories with gauge symmetries. Like, you get this funny cohomology, and it looks like de-Rham on something, but you don't know on what. And then in that case, you can just prove that, there exists some other manifolds with the property that this funny cohomology you constructed was secretly de-Rham on that manifold all along. which is great. I mean, in that case, it has a very clear physical interpretation what the manifold is. Here, because of this connected components thing, I don't think that will work, but you might have some modification of it. It might be that, oh, this thing was like some truncation of de-Rham on some other manifold where you threw away the top and bottom components. Or maybe it even hints that this was not the right cohomology to use, because like Tom has come up with like 4 different cohomologies on this thing. Like there's this one, which we call the entanglement cohomology. Then there's GNS, which you can do GNS left or GNS right. There's 2 more cohomologies. Then he has an annihilator cohomology. Then he has this projector cohomology. Like dude just has like cohomologies out the wazoo. Maybe one of those is more properly the one to think of in terms of finding a manifold for this thing. I don't know, but I mean, one of them I think is going to be the right way to think about this.
And maybe just a random, maybe unrelated question is, how could this relate to maybe statistical physics or statistical mechanics?
There was that paper on. I mean, there was that paper on there was something to do with persistent homology, but.
Oh yeah, maybe a question I think I asked Greg maybe was like, what do these cohomology classes tell us about decoherence maybe of the entanglement? Maybe if it tells us like the rate at which some entanglement state will decohere or something. I don't know.
Okay, sorry, it looks like Arcan has to go. So, okay, I'll stop the recording here, and then we can